Okay, so I've performed PCA a few times, and I've kept telling you, don't worry about the code yet. Um, let's worry about the code now. We'll see PCA twice. We'll see it in standard Python, and then we'll see it using PySpark. But in this video, we'll just look at standard Python on my desktop. So in data analytics, certain data sets become canonical to the point where they get included with pa- packages and libraries and stuff. So you saw the Palmer Penguin set back in Math 200. That's a canonical data set. It gets used in classes across the country. I'm going to use some iris data set. So the iris is the flower. I'm going to import it from sklearn. You see, this is a low-dimensional data set. It contains some measurements taken of irises, and it stores sepal length, sepal width, petal length. That's not showing, but it's there. Petal width, and then the species of the iris. So this is not big data, but it will allow us to demonstrate this big data tool perfectly well. In particular, we've got all these numerical columns. They all relate to the size of the iris. So intuitively, it's likely that these things are correlated. And if all of these columns are correlated, maybe we don't need four columns. So let's use PCA and let's see if we can capture the variance in this data set using less than four measurements. Okay, so the next thing we are going to do is we are going to import standard scalar, and we are going to hit our data with it. So what am I doing here? Well, suppose you have vectors that look like this. If I asked you about variance in the data, we as human beings would probably say, well, these first terms are very different. So are these second terms, these third terms, these fourth terms. These last terms are almost identical. From 100,098 to 100,000. And we would probably think that way because it's easy for us to just look at that and intuitively see that on a relative scale, these last terms are similar. I mean, formally, we're seeing a huge mismatch between these, which are significant, and this, which is extremely close to one. Well, this matters because PCA is based on variance. So if you just naively perform PCA, the PCA algorithm won't see things on a relative scale. The PCA algorithm will say, well, the difference between this and this is 98. That's bigger than any of the other differences. So this last entry will dominate the PCA, even though looking at it relatively, it's the least significant. So what this line of code, or what the several lines of code are doing, is that they are scaling the data to avoid issues like that. After we've scaled the data, actually performing PCA is trivial. It's just a couple of lines. There's a dedicated PCA thing that we can import from sklearn, and we perform PCA just like this. Of course, at the moment, we're just doing it. We're not looking at or interpreting our results, but we have performed the principal component analysis. How many components do we want? Let's look at a scree plot. Again, the word scree doesn't show up in the code. I mean, except for the thought title, but this is what we're doing. We can call for each component. We can call directly the amount of variance that that component is explaining. And then we generate this graph. And it's hard to see with only four possible components quite where an elbow would be. But one component is enough to explain over 70% in the variance. So that's that's a lot. And I would say that for a lot of applications, one component is probably all we need. We can also see the following. So what the PCA is the PCA is a linear combination of the original variables. And to clarify that, let me run this code. Over here, we get these numbers. This tells us that to find the first principal component, we take the sepal length, we multiply it by 0.52. Again, that's from this row. Then let's see, I'm in Notepad. Then we subtract 0.27 times the sepal width. We add 0.58 times the petal length, and we add 0.56 times the petal width. So this is how the first principal component is defined. In terms of the code, there's no mystery. These coefficients, which are called loadings in this context, are stored here. So sort of there we are. We've taken four variables and we've used them to define one variable that explains about 70% of the data. We still haven't seen a really good, I mean, we've looked at pictures, but it's still maybe not clear what we do with this. We'll see a very concrete example doing linear regression shortly.